another GRE Office Hour. If you're watching this live or after the fact, you'll see that what I do in this office hour is I go over questions that my students have. These are a combination of students from, 1 second, combination of students from my self-paced course, as well as my live online course. So we have a couple people supposed to be joining us. I'll keep an eye on the waiting room, but for now, AN is the only one here. So we'll dive right in. And AN is going to post some questions, which I will share on my screen. Just had it right here. There we go. Okay, so yeah, this is the famous baseball team question that everybody loves. So here goes. In the first half of last year, a team won 60% of the games it played. In the second half of last year, the team played 20 games, winning 3 of them. If the team won 50% of the games it played overall last year, what was the total number of games the team played? So I'm not gonna sugarcoat it. This is not a straightforward question. There's no like secret little sneaky trick I can use to solve it. So I'll come at it a few different ways, and I'm actually going to start with the algebraic way, which is not my usual sort of course of action. But in this case, I think it's probably the best. So let's write it out this way. In the first half of last year, the team won 60% of the games that it played. Um, I don't know how many games they played in the first half of last year, right? So let's call the first part X. And if they won 60% of the games, right, that means that they won 0.6 X games, right? 60% of the games. So just to explain this fraction, this is on the top, I have the number that they won divided by the number played. And this is the first part of the season. Now, in the second part of the season, the second half, they played 20 games. So I know that they played 20 games in the second half of the season and they won 3 of them. So that part's actually pretty straightforward. Now, this is one big fraction because this describes the whole season. The number of games won over the number of games played. Now, 0.6x plus 3, right, is the total number of games they won. And x plus 20 on the bottom is the total number of games that they played. And this fraction has to come out to 50% or 1 over 2. So I'll take like a beat there to just let people digest this. And AN, if you have any follow-up questions about what I've set up so far, feel free to ask.
Why don't you have to put 1 over 2x on the other side of it?
Great question. Because of what X stands for. X stands for the number of games that we played in the first part of the season. 1/2, 1 over 2, is the ratio of games won to games lost. So, I probably should have started out by writing this. Like 1 over played for this team is 1/2, right? The number of
Mhm.
games they won over the number of games they played is 1/2.
Okay.
And then I can set this whole mess up over here, right? And so this is the equation that we need to solve. 0.6x plus 3 over x plus 20 is equal to 1/2. And when I have that situation, I'm going to put these in parentheses like this, boom, boom, boom. I'm going to cross multiply, right? I multiply
Mhm.
the top left by the bottom right and the bottom left by the top right.
I had
Well,
another question.
okay.
Why could you add x plus 20 instead of doing it 0.6x over x plus 3 over 20? Why can you just put them both? on the numerator and denominator and combine them if you don't know what the denominator is for x.
So just to repeat what you said, could you just repeat that? Why couldn't I do?
Why can you combine the numerator and denominator if you don't know that x equals 20?
Oh, good question. I'm not doing that.
Okay,
As
okay,
these aren't separate fractions that I'm adding together. Think of this as one big super fraction,
okay,
right? Where I'm adding up the number of games played on top and I'm adding up the number of games played on the bottom, and that all comes out to one half,
got it, got it.
right? So then the cross multiplication we do, right? We multiply this by 2, and we get 1.2x plus 6. And then over here, I get x plus 20, like that. And then I subtract x, or 1x from both sides. I get 0.2x equals 14. And I think when I divide that by 0.2, yeah, I get 70. However, this is what makes this question extra fun. That's not the correct answer, right? 70 is not the correct answer. X represents the number of games we played in the first part of the year. The total number of games that we played last year, which is what it's asking for, is 90, 70 plus 20. So that's one way to do it. It's not the only way, but it is the algebraic way. And obviously the hardest part is setting up the equation here. Any questions on that? And then I'll explore a different way to do this.
So could you explain how you got to 90 again?
Yeah. So I solved for x, right? And I got
Mhm.
70. What does x represent?
The number of games for the first season.
Right. For the first part of the year.
Oh, yeah, but then you have to you're
And
looking for the entirety, so 70 plus 20 equals 90.
there's one last little opportunity to trip on right before the very end.
Hmm. Okay.
Right. Okay, so here's another way to do it, right? Which is to use the answer options. And I'll admit this is a little clunky. It's not great, but I would kind of just start in the middle and reverse engineer it. I would say, okay, what was the total number of games they played last year? Let's pretend they played 80 games last year. If they played 80 games last year and 20 of those games were in the second part, that means that 60 were in the first part. Well, I know that I won 3 out of these 20, and I won what was it, 60% of 60. So we can use our calculator. That's 30,
36.
right? And what I get is 39 out of 80, which is almost half, but not quite. And I can, from there, actually eliminate A, B, and C because um, I need it to be bigger. I need to have more games. Does that make sense so far, Ann?
Yeah.
So then I go to 90 and I say, all right, well, 90, I played 20 in the first part of the year, 70 in the second part of the year. Or sorry, 20 in the second part, 70 in the first part. I won 3 of these. I won 60% of these, which is 42. And that's 45 out of 90. And that gets me what I want.
Okay.
Right. So I don't know, potato. Like it one way is fast, but sort of like intuitive. The other way is like formal and like logical, but long.
Yeah, no, I totally get it. I actually like when I was doing this problem, I had reverse engineered it, but I
Mhm.
think it was because I was like actually doing the test that I just forgot the 20. So I
Mm,
started off, I didn't like think about the 20 and then subtracting it to get like 70 and doing it from there. So, yeah, this
got
makes
it.
a lot of sense.
Got it. Excellent. All right. Still keep an eye on the waiting room and my inbox just in case anyone else pops in. But AN, feel free to post your next one. Here it is. Ooh, this is a good one. Yeah, I know this one. can see how exciting my life is when, like, how excited I get at like one of my favorite GRE questions. Um, another good tough GRE question. So let's take a look here. Figure below is a regular octagon. A diagonal of an octagon is any line segment connecting two non-adjacent vertices. So just as a definition, right? This line that I just drew is a diagonal. This line that I just drew is a diagonal. This line is a diagonal, but that is not a diagonal because they need to be non-adjacent, right? Just getting some vocab down here. And it's a quant comparison. So we want to know the number of diagonals of the octagon that are parallel to at least one side of the octagon compared to the number of diagonals of the octagon that are not parallel to any side of the octagon. Let me start by saying this, and I'll use a fancy word here. These two are mutually exclusive. What does that mean? Well, it means that if I have a parallel or a line, a diagonal that's parallel to one side of the octagon like this, it's parallel and it's not parallel, right? I'm sorry. Yeah, it's parallel and it's not parallel. In other words, if a line is parallel, then it's not parallel. And if a line is not parallel, like this, it's not parallel. I know that's almost like by definition. Anyway, that's going to come into play in a second. Here's, again, a few different ways to approach this question with the caveat that it is like probably one of the toughest questions I've ever seen. It's tough because if you were going to draw out all the diagonals, you would be here for a very long time. But here's one way we could do it. Let's take 1 point in the octagon. 1 point. That one. And let's draw all the diagonals that can come out of that point. So I'm going to start here. Of course, this isn't a diagonal. That's an edge of the octagon or side of the octagon. That's a diagonal. That's a diagonal. That's a diagonal. That's a diagonal. And that's a diagonal, right? So I've just drawn all the diagonals that I can from that point. Now let's look at these diagonals and kind of label which ones are parallel and which ones are not parallel. So we'll start with this first one right here. Is that diagonal parallel to a side of the octagon? Well, I can look on the other side too. It's not, right? That diagonal is not parallel to another side. And AN, feel free to jump in and pause me if what I say isn't making sense here. But that first one is not diagonal to the other side, or parallel to the other side. Well, this one, though, is, right? This line, straight up and down, is parallel to that side. The third one is not, right? I'm just looking at this right here. Is not parallel. It's not parallel over on this side. It's not parallel over on that side. This one is parallel, straight up and down. And this one is not. Okay, so let's say we sampled this octagon. We took one vertex of this octagon and sampled it. We drew the five diagonals that come out of that. Of those five, 3 are not parallel, and 2 are parallel. Now, here's the big jump. What kind of an octagon is this? Is there anything particularly special about this octagon?
It's a regular octagon.
Right. And what does that mean?
That it is equal for all angles.
And sides.
Sides.
Right. So if I were to rotate this to each one of its 8 sides, I would have the exact same picture. And so if I extrapolate this out, there are going to be more non-diagonal sides than, sorry, not, I keep saying diagonal. There are going to be more non-parallel sides than there are parallel sides. Oops.
So could we assume like every vertices would have three non-parallel diagonals and two parallel diagonals? We can say that, right? Because it's a regular octagon.
Yes, because every, it doesn't matter which vertex you pick, you're going to do the same thing.
Okay,
Yep.
got it.
So that's one way to do it. Another more complicated way to do it would be this. Oops, sorry, one second. Another more complicated way to do it would be as follows. Um, Pretend I have 8 people in a room. And this is a classic combinations question. I want to calculate how many handshakes I can have between these 8 people. So the formula for that, and AN in our class, we haven't discussed it yet. So if it's not, fresh on your mind, no worries, right? Is going to be the NCR formula, the N choose R formula, where I have the number of people that I'm choosing from and the number of people that I want to choose. So if I want to calculate how many handshakes I can make between 8 people, that's going to be 8 choose 2. And I'm using handshakes because that sort of illustrates what I'm talking about here, right? Like that's a handshake, that's a handshake, that's a handshake, et cetera, et cetera, et cetera. So if I want to calculate all the different ways these 8 people can shake hands, it's 8 choose 2, which is 8 factorial over 2 factorial times 6 factorial. Again, if you're not familiar with this formula, we're introducing it right now. And then this can cancel down to 8 times 7 over 2, right? Because the 6 cancels out over there. And that's 54 over 2. And that is 56 over 2. There we go. You knew something was wrong. And that is 28, right? So there are 28 connections between these 8 vertices. However, some of those connections don't count, right? We're not counting that, we're not counting that, we're not counting that. So we then have to subtract out 8 of these handshakes, meaning that right? Um, the total number of diagonals is 20. Okay, now if there are 20 diagonals, you can tell I started with the easier way first. If there are 20 diagonals, let me draw all the parallel diagonals. 1, 2, 3, 4, 5, 6, 7, 8. All of those are the parallel diagonals. Well, if 8 of them are parallel, then 12 of them are not parallel because there are 20 overall. I don't love that way. I think it's needlessly complicated. Any questions on that, Anne?
Yeah, that makes sense.
All right. Let's keep rolling here. Triangles. So just to kind of categorize this question. Oh, it's a fun little picture over there. I just noticed this person in the side. GRE would be a lot more enjoyable if they have little cartoons on the side. Anyway, so just to categorize this question real quick, clearly geometry, right? Because we have a circle, and very importantly, quantitative comparison. And we always want to leverage the format of the test against the test, right? Like we know what quantitative comparison is and kind of what it's about. So let's take a look at this one. H is the midpoint of IG right there, right? So we could say, if we want to get all fancy, that those two are equal. J is the midpoint of IK. Now, I don't know yet that this is equal to that. So I'll use a different color and number there, right? So those are equal to each other. And they certainly they don't look equal. Can't trust our eyes necessarily, but we'll go from there. We know that IG equals GK equals 10. Okay, so now we know. Oh, no, I'm sorry. We know this is 10, right? That's 10. And this is going to be 5 and 5. The question is, what's greater? IJ, this little piece right here, or 5? When it comes to quantitative comparison, we want to have almost like a rebellious attitude of, I'm not looking for something that works. I'm looking for something that doesn't work. So how do we do that? Well, first things first, could I make this 5 and 5 without violating any conditions? Like, is this, if I made this 5 and 5 and just made this a nice equilateral triangle, have I broken anything that they've given me?
No.
No, right? As long as I haven't violated any of the conditions that they gave me in the instructions here, this is one possible outcome. There's nothing against it. That's the mentality we want to have. There's nothing saying we can't do it. I'm dating myself a little bit here. Air Bud, the one where the dog plays basketball. The whole premise of that movie is like there's no rule that says that dogs can't play basketball. So 5 and 5, this is one potential outcome. And as always, on quantitative comparison, we want to kind of give ourselves a little intermediate victory on the way. I just found a case where these two are equal, where IJ equals 5. Which answer options can I now eliminate?
Um, A and B.
Gone, right? Because I just found one case where they're equal. So quantity A is not always greater. There's a case where it could be equal. So now let's go back to the drawing board. And I'll just ask, could you, or do these have to be equal? Could you come up with a different, so there's 10, right? And 10. Could we come up with a case where they're not equal? Well, how about this one? It's a little more dramatically drawn, where this is I, J, K, G, and H, right? Clearly, in this version that I've drawn, which again doesn't violate any conditions because this is 10 and this is 10, but these are smaller. I don't even need to give a number. I can just say these are not equal. And that means the answer is D.
Did you also use like the logic that for like the entirety of the triangle, one of the sides has to be less than the sum of both of the sides and um it has to be greater than difference. So like IK has to be between 0 to 15. So it could really be any number from there.
Zero to 20, right?
0 to 20. Yeah, 0 to 20.
That's a true statement, but it's not necessarily helpful because that basically means like this is the range it has to be in. It doesn't mean I mean, in this case, it does, but we can't assume it could be any number in that range. There could be some other rule that comes into play here. So triangle inequality is not I mean, it's helpful to know, but it's not what seals the deal in this case. What seals the deal is the fact that we can find conflicting cases, right? Where these are equal or they're smaller.
But how do you know that they can be smaller though? Because no one said that they're equal to a certain number.
N-
Like
oh,
IK,
yeah,
they never said IK was like equal to a certain number, right?
they never said that. So I'm gonna flip the script on you and say, why couldn't they be smaller?
Yeah,
Right? Like that again is the sort of quantitative comparison mentality that we want of like as long as I obey the constraints that they give me here, and this is for geometry quantitative comparison in particular, stretch it to its limit visually. Like they've given us something that looks kind of like an equilateral triangle. I mean, like it looks maybe a little tilted to the right, but the way to really, really stress test a quantitative comparison geometry question is to try to redraw the picture like radically differently, but keeping all the constraints in place. And that usually reveals something about it.
got it.
Yeah. Um, excellent. Let's keep going here. Oh yeah. I'll mention and like and these were all from the advanced the second
Yeah.
advanced section. Yeah. Yeah, these are good ones. Okay, great. So first off, just a strategic point, and I think I've made this point before. This is a wordy question. And it may end up being easy, right? Like conceptually, it may end up being like an easy question. And I would say it's like on the easier side conceptually. The problem is it just takes so darn long to actually understand what it's asking for. And so if you didn't on the test, this is one I would certainly consider skipping. Like not skipping forever, but like I'll reframe that, deprioritizing, right? Maybe you do all the quick quantitative comparison questions first, and then once you have time, you dig into this if you have like 2 or 3 minutes left at the end. Okay, so Kelly took 3 days to travel from city A to city B by automobile. On the first day, Kelly traveled two-thirds of the distance from A to B, and on the second day, she traveled two-thirds of the remaining distance. Which of the following is equivalent to the fraction of the distance from city A to city B that Kelly traveled on the third day? So one thing that I always like to make a big deal about is using the answer options to guide us. And in this case, AN, what do you notice about the answer options?
They just get longer.
Yes. What do you notice in common about them, though?
They all have the same numbers.
Yeah, or like a lot of the same numbers,
Yeah.
right? So we start with a one minus, and then we go from there. They all start the same way, and that's worth noting because we're kind of using this to like reverse engineer the problem a little bit. Now, if you don't have any idea on this, that's okay, but I'll just ask, do you have an inkling what this one is all about in the context of this problem?
It's like the end point. It's like what you have subtract from, since you're going from a distance from like city A to city B.
Yeah, it's like the whole,
Yeah, like the end all be all. Yeah, like the
right?
whole.
Because we're talking about fractions. So we could say, all right, city A to city B is 1 mile, call it, right? City A to city B is 1 mile. On the first day, she traveled two-thirds. Oh, I should also note up to this point, right? They're all identical. It's one minus two-fifths, right? So the first day she travels two-fifths of the distance. That's like here, two-fifths of a mile. And then she travels 2/3 of the remaining distance. Well, what is the remaining distance? If the whole thing is 1 mile and I already traveled
The
2/5,
remaining distance is 1 minus 2/5.
right?
And so it'd probably be D, huh?
C or D, we'll
C or
see.
C or D, yeah.
And it's 2/3 of that remaining difference. Oh, sorry, the numbers are really small there. D is the one that's 2/3, right? So
Yeah.
2/3 of the remaining distance, and we've basically just solved the problem,
Okay.
right? Like this is one, there's not much, I mean, there is math because you're dealing with fractions. It's almost like pick out the, it's almost like a matching problem, if that makes sense. We want to
Yeah.
match the description in the question to like the numbers that are there. And that's all this is.
Mm-hmm.
I don't have much better way to do that, unfortunately. I mean, you could do if you really wanted to.
To be honest, I think I just got tripped up on like the fractions and like looking at all the numbers.
Yeah.
Um, I can do it. I think it was just like with the time crunch and everything, like the numbers can trip you up.
Yep.
So,
Yeah. Excellent. All right, let's keep going. Ooh, yeah. All the greatest hits today. Okay. So perimeter of a square S is 40. Square T is inscribed in square S. What's the least possible area of square S? So let's do this. Do they let me draw a square? It's just rectangles. Okay. I can tell I'm a little bit of a perfectionist. Just a little bit. 201, 202. There we go, 201. Good enough. We'll accept it. All right, so there's my square, my perfectly drawn square. Let's talk about what it means to inscribe a square in a square, because that's usually the area that people get a little tripped up on here. An inscribed square means that the four corners of the inside square are touching the outside square. Boom, like that, right? So I'll start with a few like guiding questions. AN, how many inscribed squares could I draw in this bigger square?
in like the big square,
Yeah, like how many of these red squares could I draw in here?
mm, in like in a good amount.
Is there any limit on the amount of squares I could draw in there?
There is a limit, I think.
What if I draw an inscribed square and every time I want to draw another inscribed square, I go half the distance?
So it's like an infinite amount of squares.
There's no limit, right? I can draw an infinite number of inscribed squares. Go to every little millimeter point along here, and I can always draw another one. But, and this is kind of inherent in the way the question is asked, there's going to be one square among those infinite squares that has the smallest possible area. I'll just say it's worth noting any extreme language in general in questions. This goes for reading and quant, or verbal and quant. So again, I'm sort of just I'm wading in here a little bit. and saying, all right, there's an infinite number of squares, but one of these squares is going to have the smallest possible area, right? Or I'll reframe that. There is a way to draw the smallest possible area. So let me go back to the first few kind of like squares I drew. I drew like one there, like this, and one maybe like there. Now, what's happening to the size of the squares as I keep going here?
They're getting smaller.
They are. But if I keep going, eventually they start getting bigger again. Oops. Because if I go all the way, then like I'm back to big squares, and eventually I get bigger. So the question is, and I'm asking this question not like rhetorically, where do things change? I'll reframe that. Where's a reasonable place to expect that they might change?
In the middle?
Right? And I'm not saying that that's true. I'm saying, given that we start big, get small, and then get big again, maybe, right? Like the exact middle point is where the area of the inscribed square is minimized. Now, the way to sort of confirm that for yourself is to say, let me start right here. And if I move anywhere from this point, I'm going to be drawing a bigger inscribed square, right? Like that inscribed square is bigger because it's traveling a further distance than the one in the middle. So, and this, I don't even know if I would call this a rule, but we can kind of make it a rule here. The area of an inscribed square is minimized in the middle of another square.
Okay, so like when they ask for a minimized like inscribed square, you can always just go towards the shape.
Yes, but this is like the only question I've seen where they've done this.
Okay.
So it's a rule, but unless this exact question comes up, it's not of much value.
Mm-hmm.
Um, so let's again, without even having to assume that this is the middle point, let's just say this. Let's just say I this square exists, right? This middle square exists, and it has a what do we say, a perimeter of 40, so 10 by 10. Well, if it's smack dab in the middle, what's the distance of that leg right there?
5.
And 5, meaning that this is what?
5 root 2.
5 root 2. And if a square has side of 5 root 2 and 5 root 2, then what's the area?
Um, 50.
Yeah, right. So at the very least, I have found a square that's 50. And try as I might, I can't get smaller than that because again, if I rotate it in either direction, it's just going to get bigger again.
Mm. Okay, that makes sense. I think it was I was tripped up, but I was like how to actually draw the triangle or no, draw like the square inside the square. Like I didn't
Yeah.
understand how to do that.
In,
So,
inscribed means all vertices are touching. So like if I don't know, if a triangle is inscribed in a circle, then we're talking about something that looks like this, right? Or if I don't know, a square is inscribed or a pentagon is inscribed in a circle, then all 5 sides.
okay. Um,
All right.
I got this question right, but I honestly guessed, so I wouldn't consider it like getting it correct in a way of like solving it. So,
Yeah. This is very similar to the triangle one we did. And it's good to kind of reinforce this because it's geometry quantitative comparison. So we have these three circles on their centers on line segment PQ. Sorry, three circles with their centers on line segment PQ are tangent at points P, Q, and R. Tangent just means touching, right? So like what that's saying is that these two points are there, these two circles are touching there, and those are touching and those are touching. So that's something that we have to assume, right? The circles are touching. We can't draw this so that they're not touching. Um, we want to know what's greater, the circumference of the largest circle, so the big one there, and the sum of the circumference of two smaller circles. Well, again, let me just try a test case. It told me that the centers of these circles are on the line. So I'll do this in red. That's the center of the left circle. That's the center of the right circle. And I don't know where the center of the big circle is. It might be R, but R doesn't have to be exactly halfway between, right? In fact, the way it's drawn, it kind of looks like the left circle is a little bigger than the right circle, so R might be a little more over there. But AN, can you give me a distance for PQ?
um, it'd be the diameter of the bigger circle.
Yep. Can you give me a sample number?
Um, 2R.
Not a variable, but a sample number.
A sample number, 4.
Love it. So, and again, it's really important to get comfortable. I'm not even going to say breaking rules. There's no rule that says PQ has to be any particular distance, right? It has left that door open. So let's just call that 4. The diameter of this circle is 4. So what's the circumference of the big circle if it's 4?
4 pi.
4 pi, right? In this one particular case, not saying it's true in every case, but in this one particular case, the diameter is 4 pi. Now, given that we've kind of chosen 4, what value could PR and RQ values could PR and RQ be?
Um, 1 and 3.
3, right?
Mhm.
Again, I'm not saying it's always this way. I'm just trying one possible case to see what happens. So if we go down this path and say, all right, PR is 1, the diameter of PR is 1, what's the circumference of PR?
Um, 2 pi.
Mm,
If the diameter, it would be 1 pi.
pi, right? Or 1
Pi,
pi.
yeah.
And what would the diameter of this one be? Or sorry, the circumference of this one.
The
If the diameter,
circumference,
yeah.
3 pi,
3 pi. So the sum of the two smaller circles is what?
4 pi.
4 pi. Okay. I just found one case where they're equal. Which answer options can I eliminate?
A and B.
Gone. Right. Now let's go back to the drawing board and try to break that example. So let's pick a different, we don't even have to pick a different number for PQ, but let's just pick a different number for PQ. Why not?
8.
8. How about 100? And
100. Okay.
8 is not wrong, but I want to get in the habit of like really, really bending things as far as we can. Because 8 is kind of close to 4, but anyway, 8's not a bad number. I just want to plant that seed. So let's make that 8. What do you want to call PR and RQ?
If it's 8,
Yep,
6 and 2.
6 and 2. I'll just comment. I like in this case that you've switched which one is bigger and you use different numbers, right?
Mhm.
I always say this, the more extreme your test, the more wonky the number you test, the more confident you'll be in the result after the fact. Because if you pick a number that's like, kind of the same, you might doubt, like, oh, maybe I just picked a number that was too close.
Mm-hmm.
So, what's the circumference of the larger circle here?
8 pi,
Pi. What's the circumference of this circle on the left?
6 pi,
Pi, and the circle on the right?
2 pi.
6 pi plus 2 pi.
So it'd be equal.
Well, I'm going to mess with your head a little bit here. Did you test enough? Or would a different test change this?
Um, I mean, we could test an extreme number like you mentioned.
And the way to avoid having to do that is if you can articulate based on these last two tests why it will always be equal.
Because PQ is always going to be equal to PR to RQ.
Exactly. Exactly. So in that case, we don't need another number. And like I said, messing with your head a little bit, there's no right or wrong answer to that. There's no right or wrong answer to like, do I need to do another test? It really is, do I feel confident enough in the test that I had? But what I will say is, rather than doing like a normal number, a less normal number, and then an extreme number, let's just do a normal number, then an extreme number.
Mm-hmm.
The go right to 100 or 1,000 or a billion or whatever.
Yeah.
Um, Excellent. Okay.
Mm. There's a head involved in this one. Sorry.
No, no. Did that just come on the thing or is that
No, this is like a PDF of the power, like the test, because I couldn't go back to the answers for some reason. So I found a PDF of it somewhere online.
oh, this one. I'll just say about data analysis questions, like very often when we do reading, one thing that you can always rely on is that the passage will be well written, right? Like you don't get you don't get reading passages with like bad grammar in them or like, clunky writing. But for data, sometimes I look at these graphs and I think like no one in their right mind would choose to represent this way. This is just like it's a confusing way to represent it, and it's kind of annoying. That's kind of the case with this one. Okay, so we have this graph shows the percent changes in the annual city tax revenue for 5 cities from 1995 to 2000. The annual tax revenue in city B was 800,000 in 1990. What was the annual tax revenue in city B in 2000? So, we're talking about city B. We can kind of map this out. In the year 1990, they had the revenue was $800,000. What this graph represents is the percent change between these 5-year periods. So if I look at city B, this tells me that from 1990 to 1995, they lost 15% of their revenue. So what was their revenue in 1995?
Mm. It would be 9. So my thought process is that if they lost 15%, then that would mean that 800,000 would have been 85% of the number in 1995.
Uh, well, sorry, 800,000 would have been, well, no, we lost 15% from 1990 to 1995.
Oh, okay. Never mind. It would be 680,000.
Yes. And again, this is kind of presented in a really weird way.
Yeah, that's why I was kind of confused on like what it actually is interpreting. Like when you explain it like that, like it makes more sense.
So then from 1990 to 2000, this darker bar here, we go up 15%.
Oh. Um,
Yeah.
so that's 782,000.
Yeah, that's it.
Got it. Okay.
Yeah. Yeah, there are, they can test this same concept in a less, clunky way. But they chose not to. They want to make you have a little fun. All right. I'd say we have time for one more AN if you have any.
I think I'm okay.
Okay, great. So I'll just do a quick little like sales pitch. Don't mind me here. For anyone watching, thank you for tuning in. If you are interested in joining for our next office hours, you can find those at my website, testprepstudios.com, where you'll also find information about my live course, which is going on at the moment. We're exactly halfway through it for my live course or my video course. Thanks for tuning in, everybody. Thank you, AN. And I'm going to stop streaming here if I can.